All right. Well, thanks everyone for joining us on today's webinar on data integration basics, focusing on spatial joins. This is the second webinar we've done on joins. We did a previous one looking at traditional relational or attribute joins, and you can check that out in our archive. But today we're going to be looking at things spatial and how we can bring things together when they have some kind of spatial relationship. My name is Dale Lutz. I'm one of the two co-founders of Safe Software, and I'm pleased to be kicking us off today. And I'm joined by my colleagues, and let's go from right to left. Olivia, why don't you introduce yourself?
Hi, my name is Olivia. I'm a developer on the geometry team, so I work on a lot of these transformers we're going to be talking about today, and I'm going to be available for a Q&A after this session.
Be sure to make her sweat, ask all the hard questions you can.
I'm Nampreet Singh. I'm on the technical support team here at SAFE, helping our FME users out with the FME desktop product.
And I'm Mark Stokes. I'm also on the FME experts team, helping people getting going with spatial relationships.
Excellent. Well, we're in for a lot of treats today. There's a lot of power that's available to you as you solve this very important problem. And I'm going to thank all my colleagues for being part of this exciting presentation and giving answers as we're going today. So we are going to look at ways today that you can maximize the value that you have in your data by combining information based on where it is and how close it is to other things. So merging and joining data sets that come from all kinds of different places using spatial nearness or characteristics can be actually quite easy. And with our product that we call FME, we can do all this work for you very, very simply and easily. So I'm going to kick it off by doing a very, very quick practical demo for you to give you a sense of what can be accomplished. So when we were back in our old office, we had Captain's Oven Pizza very close to us down on the main floor. And we enjoyed going there an awful lot, but now with the pandemic, they don't have a lot of their traditional audience, but instead they're doing takeout. And recently on a Reddit thread that was started a long time ago, this just was highlighted, Captain's Oven Pizza. And so we wanted to focus on their Surrey location and see how we could help them. So with that, let's take a look at some data and how we can help the captain cope with the pandemic by maybe figuring out what customers are near to him. All right, so what we're going to do is we're going to take a look at the address points we've got in Surrey and see which ones are close to the Captain's Pizza. So here's a data set of comma-separated values, 100,000 addresses for all the addresses in Surrey. And we can scan down to the bottom and see that it knows that it has a latitude and longitude in there, so it's going to come in spatially enabled. So I just add it to my canvas. All the fields are here. I'm in feature caching mode in Workbench, the authoring environment of FME. And I can do what's called then a partial run. So I'll run just this, and we should see all 100,000 points. Whoop, there they were for a second, but we'll go and zoom in on them in Surrey. So there we go. Here we go. All 100,000 points. There's our addresses. Mark also gave me a nice data set of drive time polygons created using ArcGIS Online of the places near to the Captain's Pizza office. And so let me just grab this and drag it on. And here I will check the parameters. That all looks okay. I will tell it that this is in LL84, the latitude and longitude, and we'll add that to our canvas. I will run this. And now if I ask to zoom to full extent, there I can see these various drive time polygons. And if I can select these, I can see these are the ones that are within 0 to 3 minutes away, 3 to 6, 6 to 9. So now we've set it up. We know our addresses and we know what's close by, and we're ready to do what we call a point on area overlayer. And to do that, I can just type on the canvas, point on area overlayer. That's one of many of these things we call transformers. I'm going to drag the points in, which are my CSVs. I'm going to drag the areas in, which are those service areas. I'm going to go in here and tell it that I do want to merge the attributes I've got, because I want to transfer the drive time areas onto the points. I'm going to run this, and now I'm going to get my 100,000 overlaid outputs. There they are. And you can kind of see that they are forming there, that both the areas and the points are there. And so now what I'm going to do is I want to just write this out for the captain so that they could do a flyer run. And so I'm going to write to Excel, everybody's favorite data set. I'm just going to put this in my temp directory, flyers.xlsx. And I'm going to say that I'll set this up in an automatic fashion. And I'm going to get what we call an output feature type. And I'm going to say that this is okay. And I'm going to connect this up to my points. And whoops, my points. And now I'm going to go and clean up the attributes because I don't really want all this. The captain is only going to send out flyers to the full address. So I'm going to say I'm going to go to manual mode and I'm going to just clean this up and get rid of those. And I'm going to get rid of all the rest of these. Oh, even some more to get rid of. Don't need any of these. Boom, I got the full address. And then what I'm going to do is go back in here and say that I'm going to create a different sheet for every one of the drive time names. So this is going to, what we call fan out. I'm going to create a different sheet for the 0 to 3, 3 to 6, so that way the captain could send different flyers out. And so I get this all ready to go. I run it, and I see that I'm pumping all 100,000 points out there. I'm going to open up this, and there's my flyers.xlsx. I'm going to bring up Excel, and there I see the addresses for the 6 to 9s, the 3 to 6s, and the 0 to 3s. And we've just done a spatial join of some drive time polygons with all the addresses in Surrey. And with that, I will head back to the presentation. So this thing I just showed you was what we call FME. FME is a tool for moving data from where it is to where you need it to be. It manifests in 3 different ways. On the desktop, we interactively create the rules that govern the transformation. And that's where you build and run these workflows. And maybe you do it just once, like I just did, and you're done. Or maybe you want to run it all the time. And if you want to run it all the time, maybe then you use FME Server, which can be hosted on your premises or up in the cloud, in FME Cloud. And then it can automate these workflows so that every time a new file arrives, it runs, or every night at midnight, it takes action and moves your data. Lastly, we have a couple of mobile apps that let you access the power of FME on your device, either to run FME Server workflows or to view your data in augmented reality. The key thing FME brings to the table, and especially relevant for spatial joins, is all these different data types. So GIS CAD, tabular, Excel sheets, CSV files, GIS files, database files, those are the bread and butter, but any of the rest of these can take part. And so the issues you might have had in integrating data because you had different data formats are off the table when you're using FME, because in FME, format is irrelevant. And so we can integrate just anything that you can throw at us. All this combines to help us in our mission, which is to help you maximize the value of your data so that your organization can make the best decisions possible. And so with that introduction, we'll get into today's agenda. We're going to look at the basics of spatial joins. We'll look at the different categories of transformers, those blue things I popped down that help you do this. There's some really interesting nuance there. And then we're going to get into some really interesting demos. And I wouldn't be surprised if the team revisits what I just showed as well. And so I think with that, I'm going to hand it off to Nampreet.
So Dale just introduced and demonstrated how FME can be used to perform spatial joins by examining the spatial relationships between data sets. Let's take a closer look at this. Our goal with a spatial join is to move columns from the join features to some target features based on the geographic proximity of those features. When looking at spatial relationships between 2 features, we're considering things like intersections, adjacencies, like our boundaries touching each other, containment, and proximity. These are often defined as spatial predicates, which we'll touch upon a bit later. Let's take a look at what we're trying to accomplish with joins in general. When working with tabular data, attributes are used as join keys to create a relationship between rows of each table, which results in a merged table. Here in this illustration, we have column C, which is being used as a common attribute to join the two tables together. Today, we'll be focusing our attention on using the geographic relationship between features as the join key instead of just the attribute. And the result will be a single fused data set. So in this illustration, we have points representing parks in the city of Vancouver, and we're joining them with the neighborhood boundaries to associate each park with its appropriate neighborhood in Vancouver.
Yeah, so how are some of our customers using these tools in their workflows? A couple of examples we've got for the spatial filter and the spatial relator that we're going to be talking about in a few minutes. We've used these extensively in one of our validation tools, the indoor mapping data format validator. So that's a very common use case for these tools is data validation. What are the spatial relationships between features, and are they matching the data model or the data schema that you have? So that's our own validator. National Research Canada, they look after our national map, and they've also done a lot of work using the spatial relator transformer to validate the National Hydrographic Network. We'll have a little look at some of that data on those ideas a little later on as well.
Yeah, also a little later on in the webinar, we'll be demonstrating how to use the nearest neighbor approach to attach text to the closest feature in a CAD to GS workflow. Some other nearest neighbor use cases that we've seen from our users, say at the Iowa Department of Transportation, they assign assets to the nearest route. So say, they have street signs and they're able to associate that with the nearest roads that they're next to. In the telecoms industry, we see cell antenna network management, and over there they try to identify which cell antennas are nearest neighbors to each other. Other telecom applications with the nearest neighbor approach can be with phone billing. So we've seen that where if a call is connected through, say, the 3 closest cell towers closest to your home address, that call would be considered a local call. So we can find the cell towers which are closest to the house address, and then resulting in identifying them as local call locations.
And of course, GIS Lite, which is what Dale was illustrating in that flash demo, is very common use is which customers are inside my market area or service area, sometimes called the drive time areas. And so that's a very simple point on area overlay kind of analysis, but very common with marketing people.
Great. So FME comes with several transformers that can be used to tackle spatial joins. Let's take a look at some of these and dive a little deeper. So today we'll be focusing in on 2 categories of transformers that perform spatial joins in FME. The first being those that look at geographic proximity, or what we like to call the nearest and dearest approach. So these transformers include the NeighborFinder, the matcher, and the point-on-point overlayer. With these transformers, you have the option to set and work with tolerance values as well. If you're looking for exact matches using a variety of spatial relationships and predicates, you'll want to consider the second group of transformers, which we'll be touching upon today, feature reader, the point on area overlayer, which Dale quickly demonstrated earlier, and the spatial filter and spatial relator, which Mark will touch upon near the end.
And so we're not going to cover our destructive transformers that also do spatial joins. So these are transformers like the clipper area and area overlayer. So they alter the geometry as you pass the data through them, but they also allow you to shift attributes between the features. So we're going to leave those for a webinar at a future date.
I'd encourage you to check out the merging or joining spatial data article that's linked down below on this slide here. It's a great overview of what we'll be covering today in terms of performing spatial joins in FME. This article also includes many helpful resources on spatial joins. You'll also find this flowchart that you see here in that article, and it'll go a bit more in depth in how to use it to navigate through which transformers to use for your specific use case. So let's take a look at the NeighborFinder, the first in our list of the proximity category of transformers. With the NeighborFinder, we want to find the nearest neighbors to a particular feature. So we typically use it when we're asking the question, what's closest to me? So for instance, kind of a real life scenario for myself, our son loves riding the local transit system here called the SkyTrain. Going out with him on a full day adventure on the SkyTrain kind of makes me anxious about being able to find a public washroom when we really need one for him. So just using this as an illustration of what we would use the NeighborFinder for, we can easily use the NeighborFinder to find the closest public washroom to each SkyTrain station, just in case we're in need of one during the day. So I'll switch over to FME Workbench here to take a look at how we can use the NeighborFinder to attach text attributes to features in a CAD drawing. So let me make the switch here. So I have a workspace prepared here. I've already run it and I've enabled feature caching here so that we can inspect the data as we go along. I've got a CAD drawing of features containing traffic signals, traffic signal points, as well as associated text representing this signal ID. So if we zoom into there, we'll see a point representing the traffic signal feature, as well as an annotation point for the text feature here. So what we want to basically do in this workflow is output a GIS dataset. So in this case, we'll be writing to a file geodatabase feature class. And with our goal here is to create an attribute for each of the traffic signal features that contain the associated signal ID. So the way we're going to do this is basically start off with splitting up the features, the point features and text features using the geometry filter, and then using the NeighborFinder to find the closest text feature to each point. So just going back here, I've connected the point feature class as our base feature and our text features as our candidate features. And I've set the number of neighbors to find to 1. So we just want to find the closest neighbor to each traffic signal feature. And what we're going to do is merge any attributes together, so between any matched features there. So use the attribute manager to basically rename the text feature to signal ID, and our output will basically be a point feature class with attributes, with an attribute indicating the signal ID associated with each point. Another nifty application of the NeighborFinder, similar to what we just saw in this last demo, is to merge text elements on a CAD drawing that contain leader lines. Here we have manhole features labeled using leader lines. We can use two NeighborFinders here to join the associated text with each manhole feature. The first NeighborFinder is used here to join the text with each leader line, and the text and leader line would be one merged feature here. Then we would utilize a second NeighborFinder to associate each leader line, which now contains the appropriate label, with the closest manhole. And so in this way, we're able to associate these labels that you see here with each manhole. And when we were preparing this webinar, Dale had a wonderful way of describing how this is basically like sliding the label down along the leader line towards the target feature here. Some other cases where you might consider using the NeighborFinder might be around associating assets such as street lights to road networks to determine the location of assets on roads or associating them with measures. You can also leverage the NeighborFinder in determining which route or conductor you're closest to, say in a utility network migration workflow or in a linear referencing workflow. So just to plug an upcoming webinar, which I think Mark and a few of our other colleagues are hosting on June 1st, focused in on linear referencing. So we have a link here, and be sure to check that out if you're interested. And lastly, we've seen cases where the NeighborFinder was used to identify which cell towers were closest to each other in an attempt to help with handoffs during, say, signal outages as well. A quick recap of some of the key parameters in the NeighborFinder that you may have seen in the demo. To find all matches within a given distance, you can leave the number of neighbors to find a parameter blank. So if you, where you see the 1 here, if you leave that blank or set it to 0, it will actually find all the nearest neighbors given a maximum distance that's set. When finding multiple neighbors for a feature, FME can store these multiple matches as list attributes. So when you're doing, we're looking for multiple neighbors, you want to enable the generate list option down there. Moving on to the matcher. It's another transformer in our group of proximity related spatial join transformers. We typically find the matchers used to identify duplicate features in some change detection scenarios. However, the matcher allows you to use its geometry as a join key and accumulate any merge attributes in a list. You can also find matches based on the combination of both geometry and attribute values. So let's go into another demo to see the matcher in action. So our goal with this workspace is to take a table containing cell signal readings that were recorded over the past few years and determine the average and the average signal power and quality, and also the range in power and quality for particular locations. So what we have here is a table in a SQL Server database containing these readings over the last few years. Some of them are located, some of those readings were taken in similar locations. So what we want to do is identify those similar locations and run some stats on them. The way we do this is basically in this workspace, we're creating geometry out of the available lat-long locations or attributes that we have here, and then we're passing it into the matcher. So just looking at the end here, we've got points representing each reading. Passing that through the matcher, we are basically going to be checking geometry here. And I've set the tolerance to 10 just to group any readings that are within 10 meters of each other together as one group of readings. The other thing I'm doing here in order to merge all the attributes of matched features is to enable generate lists. So this will basically bring all the matched attributes into a list for me to work with. And so I'm going to work with the single matched output here. And what we can see, if I select one of these records and look at the feature information, we've generated a list called _join here, and we have a list of matched readings from a variety of locations. So we have one from 2016, one from 2020, another one from 2020, and we're going to run some stats on each of these. So not going to go into details of how I calculated the stats, but basically calculating the average and range of the power and quality here and outputting it into an HTML report of sorts here. Let me just open that up for you guys, and there we have it. So basically for each of these locations, we have your mean power, your range and power over those the period of data collection, and that was pretty simple to do. So a couple of additional notes that we haven't mentioned yet about the matcher. When working with lines in particular, the vector tolerance parameter that we saw there is based on something similar to the Frichet distance or the dog leash method. And you can learn more about this in the linked blog article here. You can also use the matcher to find matching 3D features, measures, and geometry traits as well.
Yeah, so feature reader is another alternative for us to do some spatial joins. In all the examples that we've seen up to now, we've had to read all of the data in the data set and then do the comparison. And sometimes if you've got very large data sets, that's a little bit overwhelming. So the feature reader is one of the transformers that lets your database do the work instead of FME. It's a midstream option, so it's a reader in a transformer, and you can join to any database or spatial format, and you can use spatial joins or a where clause within the feature reader. So you can set a where clause to choose which data you want to read, and you can select from the spatial list of spatial predicates what kind of spatial join you want to work with. And there at the bottom is where you can choose which attributes you merge onto your incoming features from your query features. I think you've got a demo for us, do you, Nampreet?
I do. So we're going to take a look back at the demo that Dale presented just at the very beginning, and look at an alternative way of replacing the point on area overlayer with a feature reader. So if you guys recall, Dale brought in two data sets, one containing polygons containing drive times from the Captain's Pizza store location, overlaying the street addresses in Surrey and finding drive times for each of those street addresses. So alternatively here, what we can do is simplify the workspace, and like Mark mentioned, let the database do the work of doing the intersection. So here I've got the drive time polygons here, and I'm feeding them into the feature reader in here. So let's take a look at how we've set this up. We're connecting to a PostGIS database to bring in all the address points in Surrey. And what we're going to do is use the spatial filter parameter to select the intersect predicate here. And this will basically output all the addresses that overlap the service areas that came into the feature reader. What we've also set here is the accumulation mode to ensure that we are joining the attributes on the output there. And what you can see here is basically for each of the points, which I'll get some context for you here. So for each of these points, we have the associated drive time locations attached to them now.
Okay, thanks, Nampreet. So a couple more transformers that we can look at are the spatial filter and the spatial relator. These two allow you to build more comprehensive spatial relationships and spatial joins using the canned OGC spatial predicates that are in there, similar to actually what's available in the feature reader. And you can also build your own very granular spatial relationships using what's called the dimensionally extended 9 intersection model, sometimes shortened as the DE9M. And along the way, you can merge your attributes. On the right-hand side here, we've got a snippet from the FME documentation that tries to explain how some of these OGC spatial predicates work with different features, whether you've got points, lines, and areas, and how they interact. So OGC touches means when the edges or the interiors of features or boundaries, as they call it, touch, and also crosses there is illustrated. The two transformers are using the same underlying technology. The spatial filter is a little easier. It's fairly similar in some ways to the point and area overlayer and what Nampreet was illustrating there in the feature reader. The spatial relator goes quite a bit further. One of the great things and key attractions of the spatial relator is that it returns that DE3M matrix for the actual spatial relation that occurred between the two features that you're looking at, the base and the candidate, or in the spatial relator, it's listed as the requester and the supplier. When you're working with these two transformers, they are a bit tricky because what comes out is kind of reversed. So on the spatial filter, you can see the green input is the candidate, but it is the candidate that comes out of the past filters. On the spatial relator, it's the other way around. So you have features going in that are requesting candidate features and making a match with those, and the information about that match is output on the output side of the transformer. So the green goes in and the green comes out. The spatial relator also returns a list of all the matched candidates. So if you've got a one-to-many relationship that might occur, you can get a full list of that in there. So a quick demo there for the spatial filter here. And again, this is carrying on from the example that Nampreet and Dale were showing earlier on. So it's our addresses. And again, down at the bottom there, you can see that we've got the spatial filter in here. I've run it beforehand, and we've got the spatial predicate and merging the attributes from the two sets of features. So we're getting the same results there. So that's just an alternative to using the point on area overlay or the feature reader. One of the interesting things about the spatial filter is that you can do, and the spatial relator actually, is that you can do a disjoint. So you can do what aren't I related to. So in this little example here, we've got some cell signal coverage maps. The purple polygons there are the cell coverages for a potential 5G network across the city of Surrey. And what we want to know is what customers aren't going to be covered by the existing towers that are there. And so the green boundary is an area of interest. So that's the first spatial filter for the neighborhood of Whalley. And so we want to find the customers that are inside or intersect the spatial area of the city of the neighborhood of Whalley. But then in the second spatial filter, what we're using is the disjoint predicate. So we're saying which of these addresses are not within the coverage area. And so that's just kind of an alternative use of the spatial filter and spatial relators. You can sort of have a negated relationship rather than a join. So this was an interesting problem that actually just came up on the FME community as we were working and putting together this webinar. It's from Jane Mason at the Ipswich Museum. They have a biodiversity information service there, and they're doing some studies on hedgerows around their area. And what they want to look at specifically are the hedgerows that do not run along a garden. So they're not a separator for a garden. And so they want to look at the hedgerows that are in green there, but not flagged by my arrows there. So what they want to do is actually throw out the hedgerows and ignore the hedgerows that run along that green garden area. So your first guess would be, well, maybe we can experiment with some of the OGC canned predicates, and one of the ones that came to mind was touches. And when we used that predicate, what we did is we got a near result, but we also get these hedgerows that just touch at the ends of the hedgerows against the gardens, and so that's not quite the result that they wanted. And this is the result they actually want, where they throwing out the orange hedges here, and these ones which do touch the gardens at the ends but don't run along the garden are the ones that are that we want to keep. Now that's actually quite a hard thing to do if you have to build this DE9M predicate. And the great thing about the feature reader, this spatial relator, is that it returns the spatial relationship between your features, and you can see the actual relationship that you get back. And so if we bring up that workspace. Here's a simple example of that kind of workflow. We've got the lines coming in and the areas, and then in the spatial relator, we can say that we want to return a list of all the relationships that we are getting back from the two inputs. And then in the list searcher, and part of that input, let me pop that open there, is the list of features. And here we have the spatial predicates. I'll just zoom in a little bit on one of these hedgerow areas. Where's our area of interest? That's in here. And so here you can see that we have a relationship between the hedgerow and the garden, and you can see that we return the DE9M relationship for that actual interaction between this feature and the garden feature. And in this case here, what we can just do is have that relationship that came back. And so that's a great way for them to figure out which hedgerows they want to work with. So Natural Resources Canada have been using these tools for quite some time. They are responsible for building the national map, and they've been validating that national map with FME, particularly the National Hydrographic Network. What they have is a feature catalog that's ISO compliant to the ISO 9110 standard, and they work with that. And then they build the relationships between all the different types of objects that they have within their national hydrographic network. So in this case, we're looking at a lake, and what kind of spatial relationship can a lake have with other objects within the hydrographic network. And so some of those spatial relationships are canned, like the touches, which is an OGC predicate. But some of those relationships they have to build up, like the touches tangent isn't a canned predicate. And so they can build that touches tangent with the DE9M. The way that works is you have on the kind of rows, the bases, and the columns are the candidates, and the relationship you want to build is described by the dimensionality of the intersection between the base and candidates. So it's pretty tricky to do, but the great thing about the spatial relator, it'll give you clues, because if you do a few experiments, you'll get back this matrix or the actual code for the spatial predicate, and you can work with that.
Though we're not covering FME server here, you can certainly take any of the workspaces we use today and publish them up to FME server to schedule or automate those workflows. On the next slide there, we have several resources to help you get started with FME server and automating your workflows.
So here we are at the beginning of the end. So again, by choosing the right transformer, you can merge and join your spatial data more efficiently with the FME. In summary, spatial joins are needed for when you want to merge data sets that don't really have a common attribute ID, i.e. doing a traditional database kind of join. There's a ton of flexibility in FME. We've got simple joins for GIS light kind of workflows, like the point on area overlayer that Dale was illustrating, proximity, like the NeighborFinder that Nampreet was looking at. And then if you want to build more comprehensive spatial relationships, we've got the SpatialFilter and the spatial relator. If you want the database to do your work, have a look at the feature reader. Should give a shout out to some of the sources of our data that we've been using, the City of Surrey Open Data Site and the City of Vancouver open data and the UK Ordnance Survey data used by the Ipswich Museum.
We have several resources online. A lot of them are on our knowledge base on the FME community, and you can go there for additional information on spatial joins, and these include articles and tutorials about many of the methods of spatial joins and transformers that we've talked about today. We've linked to some of them here. We also included a link to the NRCan presentation, which Mark talked to just a little earlier as well. To get started with FME, you can sign up for a free 30-day trial of FME Desktop by going to safe.com. And it is a matter of gathering your data, connecting to your data, determining which transformers you need to create your spatial joins, and then automating your process through your workflows or publishing up to FME server. We have a variety of licensing options. So if you go to safe.com/pricing, you can find details about our enterprise subscriptions, our more traditional perpetual licenses, and also about our cloud deployment options. Thank you for joining us today. Again, you can get a free trial of FME Desktop from safe.com. And we'll stay on here to answer some of your questions. Thanks for joining us.
Yes, thanks for joining us.
Thanks so much.